Okay, so welcome back. What I'd mentioned previously, which was that we would, or that I would upload Monday's lecture sometime later or before today. What I thought I would do instead is basically do the rest of Chapter 13 live, and then for the extra lecture, I'll upload it over spring break, and it will just be me working through a bunch of examples of these things. I thought that made more sense than having one non-live lecture that wasn't that, where I still had some stuff to cover in Chapter 13. So that's what I'll do. So basically, the extra lecture that I owe you for Monday will be I'll upload it sometime over spring break, and it will just contain a bunch of examples of the Chapter 13 stuff, especially the very last stuff, because that's the stuff that's kind of the most important, the stuff that we're doing now. So second partial stuff and what comes next. So anyway, what the plan is you're going to have another homework. It'll be fairly short, like the last one, but I'm gonna post it today. It won't be due until the Monday after spring break, but it won't take you that long to do so. I'm just being nice by giving you over spring break to do it. It's something that won't take very long. So it'll be due the Monday after spring break, and then the Monday after spring break, I will assign your second exam, which will cover all the Chapter 13 stuff. So Monday after spring break, I'll post your second exam. It'll be due like that Wednesday, and that'll be that. So that's the immediate plan. Also, after posting your second exam, sometime that week after spring break, I will post your first MATLAB project. So when I do that, I'll have a long list of stuff that I'll go over. I'll also post some MATLAB guides for those of you who never use MATLAB, and those MATLAB projects are designed with that in mind. That is someone who has never used MATLAB before. So you don't have to worry too much about that. In fact, I think you'll find the MATLAB assignments pretty easy, probably easier than your standard homework. But anyway, so that's the deal. That's the plan. Okay. So last time we had seen the second partials test. Right, so the second partial test, I'm not going to rewrite the whole thing, but the idea is that once you've found critical points, right, so if this is a critical point, for some function f, then I compute the discriminant of f at that point. So the discriminant is the double x partial at that point, times the double y partial at that point, minus the xy partial at that point squared. Right. This was my discriminant. Okay. All right. And of course, the reason for actually writing out this discriminant and computing this at a critical point was that this broke up into cases, right? So if my discriminant was positive, there was two cases that led to me saying that there was a relative max or relative min at x naught y naught. If my discriminant's negative, that meant that there was a saddle point at x naught y naught. And if my discriminant was 0, well, unfortunately, that meant that I couldn't really say anything. And I'll mention examples later that show that anything can happen there in that case. Okay. All right. And so I want to actually do a full example of this, of how I would use this. And so let's pick one. I'll just pick one out of the textbook. So nice first example is let f of xy be x squared minus 2xy plus 1/3 y cubed minus 3y. Okay. And so what I want to do with this is find all relative extrema and saddle points. Of f. Now this function f is defined on all the reals, right? It's a polynomial thing. And so if I'm told nothing else, then I can assume that, I'm doing this over all the reals. Where might this come into, where might I be doing something different? As you might recall from Calc 1 material, when you were talking about stuff like this, it became important to consider this question where you consider your function restricted to some domain, restricted to some closed interval. Okay, and we'll talk about that in a second. In general, talking about this restricted to a domain complicates the picture. Okay, and I'll talk about that a lot after I do this example. Okay, because this is important to see. Okay. So, I want to find all relative extrema and saddle points of f. So, what's the first thing I do? Before I can apply the second partials test, I have to find all the critical points anyway, right? So, those are my points where I don't know that something happens there. Something might not happen at a critical point, but the critical points are, the total list of candidate points where something might happen, right? Where a relative extrema or saddle point might occur. So I first find the critical points, and to find the critical points, of course, I compute the gradient of f, and I do that by finding the first partials. All right, so what is the first x partial of f? Let's just go term by term since this is a polynomial thing. So this is 2x minus 2y. The last two terms depend on y, so their x partial is 0. The y partial of f, y partial of x squared is 0. Y partial of minus 2xy is minus 2x. Y partial of 1/3 y cubed is y squared. And y partial of minus 3y is minus 3. Okay. All right. So there's my two first order partials. Okay. Now to find critical points, I set both of these equal to 0. So setting these equal to 0, what do I get? So if 2x minus 2y is equal to 0, and minus 2x plus y squared minus 3 is equal to 0. Now here's a perfect example of how even in finding the critical points, right, in solving these two simultaneous equations, there is not going to be a general method for doing this. And the reason why there's no general method for doing this is because there's essentially no restriction on what kinds of functions you can end up with here, right? That entirely depends on what kind of function f you have. So the idea is if you have some polynomial thing, right, that say only has like up to degree 2 terms, then what you're going to end up with is going to be some linear. It's going to be two linear equations and two unknowns. So that, of course, has a nice deterministic process you can do. But if you have anything else, right, if you have like sines and cosines or exponentials or any other thing, even in this case, it's a polynomial thing, but it's a higher order polynomial thing. And so we end up with nonlinear terms here, right? So the idea is that there's no general process for this because these equations are not linear equations typically. And so it's kind of just going to be up to you to figure out how to handle the algebra that results here. Okay. So what's a good first step when you're dealing with something like this? If you've never seen a system of equations involving things like this. The best piece of advice is to start with the simplest thing first. Okay, so simplest thing first, that is the first equation, 2x minus 2y is equal to 0. Well, if 2x minus 2y is equal to 0, what does that tell me? That tells me that 2x is equal to 2y, which tells me that x is equal to y. Okay, so the first equation tells me that x is equal to y. How does that help? Well, that allows me to turn the second equation either entirely into something that depends on x or entirely into something that depends on y. Okay, so because x is equal to y, for any point xy satisfying the first equation, what this means is it doesn't actually matter what I do here. So I'm going to turn this into something that just depends on x. So I plug that expression into the second equation, and what I get is minus 2x plus x squared minus 3 is equal to 0. I get a quadratic thing in x. Okay, so let's rearrange here. So if I rearrange slightly, I get x squared minus 2x minus 3. This might make it easier to see in the event that we end up with something nice here. So you get x squared minus 2x minus 3 is equal to 0. Does this thing factor nicely? If not, we have to use quadratic formula, which is not too scary. But in fact, this is nice enough that we don't have to worry about it. This thing factors. So how does this factor? This is x minus 3, x plus 1, right? Okay, so you can check for yourself that actually works. What this means is that, of course, if x minus 3 times x plus 1 is equal to 0, then x is 3 or minus 1. Okay. But remember, we're not in Calc 1 anymore. We're finding points, that is, ordered pairs, right, in the plane, not just real numbers. So this isn't enough, but then we recall that, oh, x is equal to y for points x, y satisfying equations like this. And so what does this mean? What are my critical points? So my critical points are the points minus 1, and 3, 3. So I get 2 critical points. All right. Okay. And so these critical points are going to be the points that I test the determinant at. I want to apply the second partials test. And so I want to apply the second partials test and plug in these 2 points. So according to everything I've said before, these are the only 2 points I have to in fact, the second partial test only works at critical points. And so what that tells you, since these are the only critical points for this function, these are the only 2 possible points where a relative extrema or saddle point can happen. Okay. All right. And so my critical points are -1, 1, or -1, -1, and 3, 3. Okay, so there's my x and y partials of f. So let's compute my discriminant, right? So my discriminant xy. I'm going to suppress the notation here for a second. So this is the double x partial times the double y partial minus the xy partial squared, right? Okay, so I need to compute the second order partials in order to proceed. So what is the second x partial of f? The second x partial of f, let's just look at this thing. I have 2x minus 2y. Taking the x partial of 2x, that's 2. The x partial of minus 2y is 0, so the double x partial is just 2. What's the double y partial? So double y partial of f, I take the y partial of minus 2x, that's 0. Y partial of y squared is 2y, so I have 2y here. Y partial of minus 3 is 0, and so this is just 2y. What is the mixed partial? The xy partial. So I can, of course, find this by taking the y partial of the x partial, or the x partial of the y partial. Doesn't matter as long as f is nice. And so let's look at the x partial and take the y partial of that. So the y partial of the x partial here, y partial of 2x is 2. Or sorry, y partial of 2x is 0. Y partial of minus 2y is minus 2. Okay. And so plugging that into the discriminant, what do I get? The double x partial of f is 2. The double y partial of f is 2y. Minus the xy partial of f is minus 2. And that's squared. And so what I get is 4y minus 4 is my discriminant. Now, in general, of course, the discriminant can be some combination of things depending on x and y, right? It's not always going to depend on one or the other. The discriminant can even be a constant occasionally. But typically, the discriminant is just going to be some function of x and y. In this case, it only depends on y. And of course, it doesn't matter too much because x is equal to y for this example at these critical points. So this is my discriminant. Now I need to plug in the discriminant, or I need to plug in these critical points into the discriminant. So let's plug in the first one. So what is the discriminant at minus 1, minus 1? So this is 4 times minus 1, minus 4. So this is minus 4, minus 4, so that's minus 8. So the discriminant is negative at minus 1, minus 1. What does that mean? So if the discriminant's negative, you might recall from those cases, you can look at last lecture, if you need to refresh your memory. Toward the end of the last lecture, I write down the second partials test, and it splits up into those 4 cases. This case, when the discriminant is negative, means that there's a saddle point that happens there. So f has a saddle point at the point minus 1, minus 1. Okay. So then the other point whose behavior we need to classify is the point 3, 3. Right. So if I plug 3, 3 into the discriminant, I get 4 times 3 minus 4. So this is 12 minus 4, or 8, which is positive. Well, when the discriminant is positive, there's 2 possibilities, right? It can have a relative max or relative min there. To see which one, I look at the double x partial or the double y partial. I can look at either. Now you might say, why does it work out that I can look at either? In these cases, when the discriminant is positive, it turns out that the double x partial and the double y partial will share the same sign at that critical point. Okay, and so even though I stated the second partials test using the double x partial, you can use the double y partial as well. It won't make a difference. But why might you want to use one over the other? Well, in this case, for instance, look, the double x partial is a constant and the double y partial is not. So in the double y partial, I have to plug in something. Now it's not hard because this is just 2y. Okay, and plugging in 3 here, I see that it's positive. But note that the double x partial is just always positive here. So it just makes it easier. I look at this, I say, oh, I can use the double x partial, so I'm just going to do that because I don't have to plug in anything. All right. So the double x partial at 3, 3 is the same as the double x partial at any other point. It's 2, which is positive. Okay. So the discriminant's positive. The double x partial at that critical point is also positive. What does this mean? By the second partials test, this means that there is a relative min at 3, 3. Okay. And so here's a nice simple example showing exactly how this process works. Okay. So what should I say about this overall process? Basically, how difficult these problems are entirely depends on the algebra you have to do at each step. So you're finding the critical points themselves. That could you could get 2 equations out of that are nastier than what we got, which could make your efforts a lot more tedious or a lot more involved. And then finding the discriminant itself, maybe that's more complicated than in our case, which just it just makes things slightly more tedious. Now, typically that's not where the difficulty is going to come in these problems. Typically the difficulty is actually going to come in later. Okay, so and we'll talk about that here in a second. All right, so that's an example of how that goes, and that's going to be how the process goes for all of these when it comes to identifying relative extrema. Okay, now we had this discussion last time where I mentioned that relative extrema are actually more important to understanding the behavior of the graph of a function than global extrema, than global maxes and global mins. They're more important for understanding the shape of the graph, and I illustrated why that is. Right? The idea was that saying where a function had a relative max, relative min, or a saddle point, now that we're in the higher dimensional case, that told you what the overall shape of the graph of a function looked like. Okay, and that shape wasn't dependent on what window I was looking at, right? So basically, knowing the relative maxes and mins, those didn't really change as I changed my window. As long as my window included those relative maxes and mins, then nothing about the shape of the graph really changed when I was restricting my attention to, say, a different window. But we saw how the global maxes and global mins could be changed by this. If I change the window that I'm looking at, I could certainly change where the global maxes and global mins happen. Okay, and there's a reason for that, right? So you might recall this fact from Calc 1. But before I get into that, I'm going to mention something else from Calc 1. So back to Calc 1 land. As I said, at the very beginning of this stuff, you're going to get sick of seeing this comparison to Calc 1 stuff over and over and over again. So I'm back in Calc 1 land. What was the deal, right? If I have a function that just looks like this, and if I don't impose any restrictions on it whatsoever, this function has a relative max and a relative min. So there's the relative max, there's the relative min. Does it have a global max or a global min? All right, we're assuming this is the graph of some polynomial thing. So this is the graph of some polynomial thing. And this polynomial thing, if I'm assuming that I'm not tricking you and it does something else out here at the ends, then you can assume that the way this looks is exactly what's going to happen. It's going to go off to infinity in this direction, go off to minus infinity in this direction. And so looking at this, it's defined on all the reals, so its natural domain is all the reals. If I talk about its global max or global min on all the reals, well, it doesn't have one, right? Because it's going off to minus infinity, so the further I go out, right, my negative x-axis, I'm going to get smaller and smaller values going off to minus infinity. Same thing is going to be true except going to positive infinity in the other direction. So it has no global max and min. But remember that there's a lot of problems that come up, optimization problems or problems where I want to know, I want to talk about optimizing some expression relative to some constraint, okay, in some way. And a lot of the times, the way that this comes up naturally is by restricting my attention to a closed interval. So here's a closed interval, AB. Okay. Now, what did you learn in Calc 1? Right, so in Calc 1, if I take a function like this, and I consider that function on a closed interval AB, what benefit do I get from restricting my attention to a closed interval AB? Someone might remember this. This is a named theorem from Calc 1. So if you remember what is in the setup here, you can say it in the chat. But the idea is that I had the Max-Min theorem from Calc 1. Does anyone remember what this said? Yeah, extreme value theorem. You may have heard it phrased like this. I think in our textbook we call it the Max-Min theorem, but extreme value theorem is another example. Or depending on exactly what you mean by that, it could be a corollary of this. But yes, this is the idea. So of course it turns out there are many versions of the Max-Min theorem, and this version is a special case of kind of the most general Max-Min theorem. So what does the Max-Min theorem say? It says I need an assumption on f. If you remember what that assumption is, you can type it in the chat. So if f is a something function on a closed and bounded interval. So what does a closed and bounded interval look like? Well, it's some closed interval AB. Now, I'll mention that again in a second. There's some subtle stuff going on here that you probably haven't considered before. So if f is a particularly nice kind of function on a closed and bounded interval, then f has both a global max and a global min. This is guaranteed, so long as f is a particular type of function. What is that particular type of function that f has to be? It has to be continuous. That's it. Okay, so it actually doesn't need to be differentiable, although in all the cases we applied this knowledge, it was. It just needs to be continuous. Needs to be continuous on a closed and bounded interval. Okay, so closed and bounded interval, in Calc 1 that looks like this. Okay, now it turns out that being an interval is not what's important here. Okay, what's important is being closed and bounded. Okay, so in the reals, these are the important quantities. Now, it turns out what's actually going on is that this being closed and bounded is really a condition called compactness. Now, a compact set being closed and bounded and a closed and bounded set being compact, so going in both directions here, that's not always true. This is a topological property. Okay, so this is a topological property. Topological property, best way to describe it is topology is a branch of math that is, you can think of it kind of like geometry, but it's floppier. It's a lot floppier than geometry. You're allowed to do crazier stuff in topology because you don't need to be as rigid as you are in geometry. You're allowed to deform things in topology in ways that you don't consider in geometry. Okay, topology is really the study of what's called open sets. Okay, and anyway, or maybe I should say topology is the study of continuity. It's a study of continuous functions. Okay, whereas geometry is a study of functions that are more regular than continuous function. They have more derivatives than the functions that you deal with in topology. Okay, so anyway, this is the notion of compactness. Now, generally, compactness is not exactly the same as closed and bounded, but there's a theorem called the Heine-Borel theorem that I'm not going to write out, but I'll just say the Heine-Borel theorem says that in subsets of the reals, and actually not just the reals, but Rn, right? So n-dimensional real space, a compact set is the same as a closed and bounded set. Okay, and so really the actual Max-Min theorem says if f is a continuous function on a compact set, then f has a global max and global min. Okay, and that's important because we're actually going to do this same exact theorem in Calc 3. We're going to have the Calc 3 version of this theorem where, of course, we're not going to have an interval here. We're going to have a closed and bounded set. Okay, now you don't have to worry about that too much. I'm going to draw what a closed and bounded set looks like in Calc 3 world so that you don't have to worry about it. But anyway, what was a fact that we used? So it was nice to say that a function, a continuous function, has both a global max and global min so long as you're talking about the function on a closed and bounded set. Okay, so you're guaranteed to have both a global max and a global min. So this is awesome because now you know that they exist, you just have to find them. Okay, so where are they? Let's look here for this particular example. So there are some candidate points, right? The candidate points are here and here. I always know that those are places where I can have global maxes and mins. Okay, but those aren't the only places, right? In fact, here we have to check the endpoints. All right, so if I check the endpoint, my endpoint here is there. Well, you can barely see it, but this is lower, right? So my global min is here. So my function f has both a relative min and global min at this point, but its global max is there. So what is it that this picture is showing? Well, this is only one example, so of course this doesn't technically prove anything, but this is illustrating what it is that can happen here. And so there was a big fact associated to this Max-Min theorem that was a global max or global min for a function f on AB, this closed interval, occurs either at a, so it occurs either at a relative max or min in the interior, I'll rewrite that in a second, that is in the open interval AB, or at one of the endpoints. And so this was exactly the process you used in Calc 1 to solve this question. So if someone posed to you the question, all right, here's a function, right? It's differentiable, so it's automatically continuous. It's really nice. It's a function. To consider it on this closed interval. Find the global max and min of this function. Okay, how would you go about solving that in Calc 1? Well, the way that you went about it is you would do exactly what you did to find relative extreme values, right? So you would do exactly what you did with the first or second derivative test. So you'd find critical points. You would do first or second derivative test to identify whether at those critical points you had a relative max or relative min. Then you would plug in the relative max and relative min points into the function. Then you would plug in the endpoints, right? This is you testing the endpoints, okay? And then you would look at a list of those values, right? So you would plug in the, so let me write all this out. So question, how would I solve the problem find global max and min for given, obviously it's continuous. It will typically be much better than that. Continuous function f on closed interval AB. So step 1, right, I would find critical points of f. Step 2, identify whether f has relative max or min at each crit point. Now, you could say if all you cared about was finding global max and min, then technically you don't need to do step 2, right? Once you found the critical points, you could just plug in the critical points, then plug in the endpoints and compare, right? The largest value will be your global max, and the smallest value will be your global min. And you know that from this fact, right? A global max or global min has to either happen at a relative max or min or at one of the endpoints. But if you have a list of the critical points, then, okay, relative maxes or relative mins can occur at some of them or none of them, but you could just plug all of them in anyway. And if you find the largest value among them, then you found the global max. The smallest value among them is going to be where your global min happens. But most of these problems are going to be multi-part problems where you're going to be asked other questions, and so it's always good practice to find where the relative maxes and mins happen. Anyway, even if you're not asked to do that. Now, of course, on an exam, you only have to do what you're asked to do, but this is just good practice when you're doing these problems. So step 3, plug in the endpoints, or plug in each relative max or min into F. 4, plug in the endpoints. 5, make a list from part 3 and 4. The largest on this list is the global max, and the smallest is the global min. So this might be, a trip down memory lane for you, but this is the process that you used to do this. Now, why am I spending so much time talking about Calc 1 stuff? Because this process is going to be exactly the same as ours. The only difference is that we're not going to be dealing with intervals. Now, unfortunately, whereas previously in this course, a lot of the times bumping the dimensions up by 1 didn't actually affect too much in the way of algebra and in the way of what we had to do. In this case, it is unfortunately going to be really nasty. It is a big deal. Why is it a big deal? So let's go back. So why it's a big deal is what we're essentially saying here. If we don't restrict ourselves to this specific case, right? If we're trying to think more generally about what it is that's going on. I have a function f on a closed interval AB. Now, as we said, we're going to replace this interval with a closed and bounded set in the plane. Okay. And so when we say that it either occurs at a relative max or min in the interior of the interval, that is still going to be fine because we'll be able to talk about the interior of a closed and bounded set in the plane, or at one of the endpoints. But what was the importance of the endpoints? It turns out that really, when we talk about the endpoints, what is the relationship geometrically to the endpoints A and B to this interval? Another way of phrasing this, one of the endpoints is this is on the boundary of the closed interval AB. Okay. This is the big problem. Okay. Because in dimension 1, the boundary of a closed interval is just two disconnected points. But the boundary of a closed and bounded set in the plane is typically a curve. Right? So two disconnected points as your boundary, there's just two of those points that need to be evaluated. But when your boundary is an entire curve, is an issue. Because a curve, of course, has infinitely many points that make it up. Okay, and so if I look at this expression here, so for instance, right, if I have a set, I'm going to call this set R. So this is a closed and bounded set in the reals. All right, here is a closed and bounded set in the plane. So this is my set R. Okay, so this is a closed and bounded set in the plane. What is the boundary of R? Well, the boundary of R is this curve. I'm trying to do in a different color here. Okay, so that curve is the boundary of R, and it's written like that. I can't remember if I've introduced this symbol for the boundary before. So del R is the boundary of the set R. Now, if you have a closed and bounded set in the plane, it has a boundary. Okay, typically, if that set is relatively nice, that boundary is going to be a curve. Notice there's infinitely many points on a curve. The boundary, however, for this set is these two disconnected points. And so the boundary of that set R is just 2 points. There's definitely not infinitely many points there. There's just 2. Okay. And so ultimately, what it is you're actually doing in Calc 1, when you find the global max and global min for a function, you are finding the max and min for the function on the interior, on what's inside, and then you're finding the max and min on the boundary, but that's just 2 points. So in Calc 1, to find that, all you did was plug in those points. And you were good to go. And then you just compared all the values, and that's how you got global max and global min. In Calc 3, it is unfortunate what happens. Because I find the max and min on the interior, on the inside, but then I have to find the max and min on the boundary. And it turns out that that is a lot harder. Okay, that is a lot harder, and it's not as easy as just plugging in points. This is ultimately what causes things to be nasty. Okay, so first, let's go back to Calc 3 land. So, we have the Max-Min theorem in Calc 3. So, the Calc 3 version of the Max-Min theorem. If f of xy is a continuous function on a closed and bounded set R, then F has both a global max and a global min on R. We have the similar fact that we had in Calc 1, which is a global max. This is a very important fact, of course. So a global max or min for a continuous function f on a closed and bounded set. BDD is going to mean bounded. So closed and bounded set R occurs either at a relative max-min in the interior of R, or on del R, the boundary of R. Okay. So this leads us to the following process. So question: how do I find the global max of f of xy on closed and bounded R? Okay, so what's the answer? Of course, this applies for max and min, so I'm going to include both of those. So, part 1, I find relative max and min. I can include finding the critical points here, but maybe I'll write that separately. Just because, as I said before, there is a shortcut here where technically you could just plug in all the critical points, but typically, as I said, in these problems, I'm going to be asking you other questions anyway, so you're not going to get off with a shortcut. So find critical points of f of xy on R. Now, the difference here is a lot of the times when we were finding critical points, we did this for functions that were defined everywhere, so we didn't have to worry about whether the critical points were actually in the set. So here, you could imagine you might have a function, right? If I draw quickly, like here, let's say this is my R, right? So it's some disk that looks like this. If this is my R, the graph of my function is above this R here, right? And that graph, this function could have critical points. Some of them are in here, some are on the boundary, maybe, but some are outside, right? So, of course, if I'm trying to find global max and min for this function relative to this set, right, on this set, then I don't care about critical points that lie outside. I don't care what the function is doing outside the set. I care what it's doing, like, on the set itself. And so I would toss out, right, those critical points. Okay, so that's something we didn't do previously, but that's what you're going to be doing for these, potentially, right? Some of those critical points you find aren't going to actually be in the set, so you would toss those out. Okay, so then secondly, find relative maxes or mins. You'll probably also find some saddle points in the mix here, but nothing's going to happen there. So find relative maxes and mins of f in the interior of R. This is step 1 to exhaustively solving this. All right. What next? So next I would find the global, or I won't say global. So find the maxes and mins of f on the boundary. All right. So in part 2, I have found a list of points, right, where relative maxes and mins happen for this function. In part 3, I found another list of points where maxes and mins for this function happen. Of course, the reason why it's more than just 2 is you could potentially have a function that, let's say it has a max value of 4 on the boundary, but there's like 10 points where it actually achieves that max value. Well, you'd have to include all those. Okay. Step 4, right? Plug the points found in parts 3 and 4 into f of xy. So this gives me a list, right? Get a list. So get a list of values of f. And then step 5, right? Compare the list in 4. The largest value is the global max. The smallest is the global min. Okay. Now note, this process is actually absolutely identical to what you did in Calc 1. The only difference is that in step 3, finding max and min of f on the boundary, in Calc 1, I didn't need to find anything because the boundary was just 2 points. And so all I did was just plug them in. Okay, so there was no finding done. And unfortunately, that is the big distinction. This part that I just circled is by far the hardest part of this entire problem. Okay, so the hardest part. Okay, everything else is like 10,000 times easier than part 3. Okay, so in general, this entire process is easy except for part 3. Part 3 is by far the hardest part. Okay. And the reason it's the hardest part is because we just don't have a good way of dealing with this. So we are, in fact, going to have to do something entirely different in order to deal with this. In fact, to deal with this, what we have to do is something called Lagrange multipliers. Okay. So what's the plan here? The plan is, on Friday, I'm going to do an example of what we would have to do without Lagrange multipliers. It's good to see that one example. Then introduce Lagrange multipliers, do some examples, and then you will have seen everything that you need for Chapter 13 stuff. So after that, over spring break, I'm going to upload a video of myself doing a bunch of these examples. And that will be all of the Chapter 13 material. So that'll be it. Anyway, so I think that's it for now. I think I'm out of time. But anyway, on Friday, basically we'll finish all of Chapter 13, especially once you've seen a flurry of examples. In the video that I post later. Okay. All right. So I think that's it for now. So I will see you all on Friday. Let's see. I had a question here. Homework 1 and 2 be graded relatively soon. Well, I'll see what's going on there because those should have been graded a long time ago. So yeah, I'll look into that. And I know I have some people email me over the weekend. I was organizing this conference. That's why on Monday I couldn't record lecture. So I'll get to those. I didn't ignore you indefinitely. I will get to your emails. So don't worry. If I haven't responded to your email by Friday, then email me again. Okay. So thanks everyone. I will see you all on Friday.